Lesson 11.3.2, Power Models. In previous lessons, we investigated the behavior of linear models and exponential models. We can use other mathematical models to describe the behavior of real-world phenomena as well. One type of mathematical model is the power model. A power model is any mathematical function of the form y equal a times x to the n, where a and n are constants. In this lesson, we will learn about linear, quadratic, and cubic power models. On the right is a language tip. A function of the form y equal a times x to the n is called a power model because it contains a variable x raised to a power. Notice how this is different from the exponential model where the variable was the power, but now we have a variable raised to a constant power. Number 1. A plastics company makes many different balls in various colors. Some balls have greater diameters than others. The diameter is the distance through the middle of the ball. The company needs different amounts of paint for the different sizes of balls. The table below shows the amount of paint that the company needs for balls with different diameters. So here we have two columns. One has the diameter measured in inches. You can see that we've got 1, 2, 3, 4, 5, 6, 12, 18, 24, and 30, just giving us varying sizes. And then in the second column, the amount of paint needed, depending on the diameter, starting as low as 0.02 ounces of paint needed for a diameter of 1 inch, all the way up to 15.70 ounces of paint for a diameter of 30 inches. And then on the right, you see a graph of those ordered pairs. Remember that each row represents an ordered pair of numbers. Diameter is one part of the pair, and ounces of paint is the other part of the pair. You can see the horizontal axis is using to measure diameter, and then the vertical axis is being used to measure the amount of paint. Part A on the next page. Do you think that there is a linear relationship between the diameter of the ball and the amount of paint needed to paint the ball? Give a reason for your answer. If we take a look at the table and the graph, I would say with the graph, do we notice a straight line? That's what it means for there to be a linear model or a linear relationship. Doesn't seem like it. So no. What's the reason? The points don't follow a straight line. The points are not in a straight line. Part B, look at the graph. How large a ball, meaning what diameter, can you paint with 4 ounces of paint? Estimate the diameter to the nearest inch. You might want to draw a smooth curve connecting the points to help you answer this question. We saw something like this in the previous section. I'm just going to connect these dots with a curve that seems to go through them. You can see that it starts to curve upwards. And they would like to know how much paint is needed how large of a ball can you paint with 4 ounces of paint? So I'm going to start with 4 ounces of paint. I have to estimate where that is. It's somewhere between 3 and 6. So I'll say that looks like maybe where 4 is. And I'll follow that over to the graph. And it looks like it maybe intersects at 15, meaning a 15-inch diameter ball. So about 15 inches in diameter. Part C, what sizes of balls can you paint with less than 4 ounces of paint? Use the graph in your answer to question B to answer this question. So if we're thinking of using less than 4 ounces, then that would have to be a diameter that is smaller than 15 inches. So we can say diameters smaller than 15 inches. This is also similar to things that we were doing over the last few lessons. And then finally, part D. look at the graph. How much paint do you need to paint a ball with a diameter of 23 inches? So going back to our graph, now they are saying that we have a diameter of 23 inches. 23 is a little more than halfway between 20 and 25. You can also see that we were given that if the diameter was 24 inches, it would need 10.05 ounces of paint. So if we think of that as somewhere near 23 also, it looks like maybe we would need about 10 ounces of paint. Again, we're just estimating by using the graph. Finding something like 23 is somewhere between 20 and 25, following that up to the graph, and it looks like maybe it's about 10 ounces of paint. That seems like a good estimate. Next steps. If we wanted to automate a machine to do this painting process for us, we could compute the actual function for this model. Each ounce of paint covers 180 square inches of surface area. The surface area of a sphere, the balls are spheres, is approximately the number pi times the square of the diameter. That is, capital A is approximately the symbol pi times d squared. Thus, the function for the amount of paint that you need for a ball is the amount of paint needed for a ball is equal to the surface area of the ball divided by the number of square inches of paint per ounce. This is giving us capital P for the amount of paint needed for a ball is equal to capital A, which is the surface area, divided by 180. Those both have the same units of measurement, square inches for area. That is approximately equal to 3.14, since 3.14 is approximately the value of pi, times d squared. Notice I'm just using my capital A is equal to pi d squared. And then that's divided by 180. You can divide 3.14 by 180, and you get approximately 0.017. And then this is the number that's being multiplied by d squared, where d is our variable, the varying size of the diameter. So we would like to have a more precise answer to the question. What size balls can we paint with less than 4 ounces of paint? We are going to use algebra to find the answer to this question. We must solve the equation capital P is equal to 0.017 d squared for d. We want to find the diameter when capital P is equal to 4. We will need to use the square root property to solve this problem. So on the next page, you can see that we start with the relationship capital P is equal to 0.017 d squared. Then we are replacing capital P with 4, because that's the amount of paint that we need. Just like we saw with other examples in previous lessons, we can divide by 0.017 first. That's using an opposite operation. So then, after we do the division, 4 divided by 0.017 is approximately 235.29. So now we have 235.29 equal to d squared. So here again we need an opposite operation. The opposite of squaring is taking the square root. So we take the square root of both sides. The square root of d squared on the right-hand side, and then the square root of 235.29 on the left-hand side. When you type in the square root of 235.29 on your calculator, you get 15.34, and that gives us the value of d. Remember that any positive number has two square roots, one positive square root and one negative square root. So technically what we did above, it would imply that we get positive 15.34 or negative 15.34 as an answer. But in this example, d is the diameter of a ball. And we always measure length with positive numbers. So this must be positive. So in this case, we are only using the positive square root. Using the solution of the equation, d equal to 15.34, and our graph, we can give a more precise answer to the question, what size balls can we paint with less than 4 ounces of paint? We see that we can paint any ball with a diameter smaller than 15.34 inches. So we can paint balls with diameters less than 15.34 inches with less than 4 ounces of paint. We can restate this conclusion by saying that balls with diameters in the interval 0, less than d, less than 15.34 can be painted with less than 4 ounces of paint. This is giving us any diameter between 0 and 15.34. Also notice how this is close to what we had said earlier. Diameters smaller than 15 inches just gives us a little bit more. We get a little bit more of an exact answer with that 15.34. You may not have thought to include the interval in your solution, since the diameter of a ball has to be a positive number. However, you should state the limitations of the variable because they are not always obvious in mathematical models. So now number 2, we will use the equation P equal to 0.017 d squared to answer the following questions. Part A, what size balls can we paint with 8 ounces of paint? Solve the equation to find a solution. Use the graph to see if your answer is reasonable. So here this is just like what we did before, except now P is equal to 8. So that means I will set 8 equal to 0.017 d squared. Just like we did before, we'll divide by the 0.017 first. When I do that, it means that I'm just going to have 8 divided by 0.017. And I'm just going to follow the same theme that they did above. After they did their division, they rounded to 2 decimal places. So I'll do that here. 470.59 is equal to d squared. And then just like we did before, after we did the division, we took the square root. So I'm going to then take the square root of 470.59, and that's going to be equal to the square root of d squared. Remember that all that happens on the right-hand side is the square root of d squared leaves you with d. So I'll have d, and then the square root of 470.59, and I'm again going to round to 2 decimal places, 21.69. 21.69. And that's our answer for D. So if we want to paint with 8 ounces of paint, we want to think of all of the diameters that would work. So we can say diameters less than 21.69 inches. Part B, what size balls can we paint if we want to use between 12 ounces and 16 ounces of paint? Solve the equation to find a solution. So now we have between 12 and 16 ounces of paint. What diameters can work? So you're essentially doing the same thing we did before, but you're going to find the diameter that works with 12 inches and the diameter that works with 12 ounces and the diameter that works with 16 ounces. And then that gives you an interval for the diameters. So I'm going to do this first with 12 ounces, setting 12 equal to 0.017 d squared. Again, divide by 0.017. So 12 divided by 0.017. That gives me 705.88. And then take the square root of both sides. And you get 26.57 is equal to D. Notice you don't have to write the square root of both sides in your work if you don't want to. You can just use your calculator. The square root of 705.88 is 26.57. And then let's do the same thing for 16. 16 equal to 0.017 d squared. First, I'm going to divide 16 divided by 0.017. And that leaves me with 941.18 equal to d squared. Now I need to take the square root of both sides. When I take the square root of d squared, that leaves me with d. And the square root of 941.18 is 30.68. And notice what this gives me. An upper amount for the diameter, 30.68, and a lower amount for the diameter, 26.57. So, diameters between 26.57 inches and 30.68 inches. Now, before we go on, let's check both of the answers in part A and B to see if we've got some reasonable answers. So first of all, with part A, we said we would like to use 8 ounces of paint. So let's go up to our graph. 8 ounces of paint, somewhere between 6 and 9. Looks like it's somewhere in the 20s. And what was the answer that we got? 21.69 inches or less. That seems reasonable. We said that we should get something in the 20s from that. And then for part B, we said we would like to use between 12 and 16 ounces of paint. So where 12 ounces is, up to 16 ounces. That should give us something somewhere between 25 and 30. And if we look at our answer, we said 26.57 and 30.68. That's approximately close to somewhere between 25 and 30. So again, this is a reasonable answer because it looks pretty similar to what we see in the graph. So now let's try these. When you drop an object, gravity causes the object to accelerate, meaning it moves more quickly. The object's speed increases as it falls to the ground. The longer an object falls, the faster it travels downward. Number 3. The graph below shows the distance that a soccer ball fell during a 6-second period of time. The distance that the soccer ball fell can be modeled by the function d equal to 4.9 t squared, where d is the distance in meters that the soccer ball fell in t seconds. Here we have a few pieces of information. A horizontal axis, time, measured in seconds, a vertical axis, distance traveled, measured in meters, and we've got some dots just showing different possibilities for distance traveled for different amount of time. Part A. Use the graph to determine how many meters the soccer ball had fallen 3.5 seconds after it was released. So just like we did with previous examples, I'm going to connect my dots with a curve to give a little bit more visualization. And then 3.5 seconds is halfway between 3 and 4 seconds. So if I start there and follow up to my graph, what does it look like the distance traveled is? Looks like approximately 60 meters. So about 60 meters. Part B. Use the equation d equal to 4.9 t squared to determine how long it would take for the soccer ball to fall 30 meters. Here, notice they're giving us d is equal to 30, which means we're going to put 30 in for d, set that equal to 4.9 t squared. And now, just like we did on the previous page, I want to solve for t. So what's the first thing that I would do? I have to get rid of that 4.9. It's being multiplied by t squared, so I have to divide by 4.9. which means 30 divided by 4.9 is what I would find first. If we want to use similar methods that we saw before, we can again just round to 2 decimal places here. 30 divided by 4.9 is 6.12, and that's being set equal to t squared. And now what would I do on both sides? I have to do the opposite of squaring, and the opposite is taking the square root. So if I take the square root of both sides, then I have the square root of 6.12 will be equal to t, and this is 2.47. 2.47. So how long would it take for the soccer ball to fall 30 meters? Approximately 2.47 seconds. Why are we using the word approximately? Because we were rounding throughout this. Does that seem reasonable from our graph? Well, 30 meters is halfway between 20 and 40. And it looks like we get some amount of seconds between 2 and 3. So 2.47 seconds seems reasonable. Part C. Suppose someone dropped the soccer ball from an apartment building window 190 meters above the ground. How many seconds would it take for the soccer ball to hit the ground? Use the equation d equal to 4.9 t squared to answer this question. So again, similar to what we just did in part B, I'm going to replace d with 190, set that equal to 4.9 t squared. Now I have to do the same steps I did before. Divide by 4.9 first. 190 divided by 4.9 is 30.78. Oh, sorry, 38.78. And that's equal to t squared. And now take the square root of both sides. Square root of 38.78 gives me approximately 6.23. So, approximately 6.23 seconds. And again, if we go up to the graph, find 190, well, that's above 180, so whatever the time is, it should be more than 6 seconds, and it looks like it is. Continuing with the same example on the next page, part D, use the equation to complete the table below. Now they're giving us values for time, and we're going to put those values in to find the distance that the ball has fallen. So remember, our equation is d equal to 4.9 t squared. So now when time is equal to 0 seconds, how far has the ball fallen? First of all, before even using the equation, just think of this intuitively. No time has passed, which means you haven't dropped the ball. So it wouldn't have fallen. So what has to be the distance? It has to be 0. But you could also find this out by just putting 0 in for t. D equal to 4.9 times 0 squared. Well, 0 squared is just 0 times itself. That's 0. And then 4.9 times 0 is also 0. So now how about t equal to 1? D would be equal to 4.9 times 1 squared. And now before you grab your calculator, what's 1 squared? That's 1 times 1. That's 1. And now what's 4.9 times 1? Anything times 1 is itself, 4.9. And now how about the rest? T equal to 2. That would give us d equal to 4.9 times 2 squared. Now it seems appropriate to grab our calculator. 4.9 times 2 squared. That gives me 19.6 meters. And then for t equal to 3, again, this will just be d is equal to 4.9 times 3 squared. So 4.9 times 3 squared gives me 44.1. And then finally for t equal to 4, d is equal to 4.9 times 4 squared. Which is 78.4. All right, so now part E. How do the data in the table show that the distance that the soccer ball has fallen is not increasing at a constant rate? We saw questions sort of like this in the previous section. If it was falling at a constant rate, you should see that as time increases by 1 second, the distance increases by the same amount. But the distance from time equal to 1 second to time equal to 2 seconds, that's the distance from 4.9 to 19.6. That's about 15 meters. But now as we increase from time equal to 2 seconds to time equal to 3 seconds, it goes up from 19.6 meters to 44.1. That's more than 20 meters. So you can see that the increase in distance is not constant. So as time increases by 1 second, we don't see the same increase in distance. We do not have a constant increase in distance. We would see that in a linear model, but this is not a linear model. So this is what this question is pointing out to us. So now another example. Number 4. A quarry is a place where rocks are dug from the earth. The brown quarry cuts stone into cube-shaped blocks. A cube is shaped like a box that has the same length, width, and height. Think of if you've ever rolled dice on a board game. Those are cubes. A cubic foot is the volume of a cube with sides that are each 1 foot long. The quarry cuts stone that weighs 168.5 pounds per cubic foot. The volume of a cube is the length of its side raised to the third power. You can use the function W equal to 168.5 times s to the third power, or s cubed, to calculate the weight of a cube with side length s. Use the function to complete the table below. Then use the table to draw a graph of the function. So first, side length is the first column, weight of the block is the second column. We're given some values of side length, 0 feet long, 1 foot long, 2, 3, 4, and 5. And then we want to find the weight of the block with those varying side lengths. So first of all, if the side length is 0 feet, again, just ask yourself an intuitive question. If you have a cube where each side is 0 feet long, do you really have a cube? What would the weight of that cube really be? Well, it doesn't exist if it's 0 feet long on each side, which means that its weight can only be 0. 0 pounds. Now, what if the side length was 1 foot? Well, then that means when s is equal to 1, using our equation, W would be equal to 168.5 times 1 cubed. 1 to the third power just means you're multiplying 1 times 1 times 1. That's just 1. And when you multiply that by 168.5, you're just going to get 168.5. Now let's start using our calculator with the next values. So when s is equal to 2, then W is equal to 168.5 times 2 to the third power. So just type into your calculator 168.5 times parentheses 2 close the parentheses, raise the power to the third power. And you're going to get 1,348. That's how many pounds that is. Now S equal to 3. W is equal to 168.5 times 3 to the third power. 168.5 times parentheses 3, close the parenthesis, raise to the power, third power. That gives me 4,549.5 pounds. 4,549.5 pounds. It's getting pretty heavy now. All right, S equal to 4 is the next one. Then I would have W equal to 168.5 times 4 to the third power. And you get 10,784. And then finally, S equal to 5. W is equal to 168.5 times 5 to the third power. That gives me 21,062.5 pounds. And now before we go on to the next couple questions, let's plot the data that we got in our table. So when side length was 0, the weight was 0. That gives me a point at 0, 0 on my graph. Now when side length is 1, the weight was 168.5. You can see that the way they've marked the weight of the block, it goes up pretty high just with a couple of marks, mainly because we have to get up to 21,000 at some point. So the weight for 1 feet in side length is pretty low, so I'm going to keep a dot pretty low vertically. Now when side length is 2, the weight was 1,348, still not that high up. We don't really see a big jump until 3. And now with 3 feet in side length, the weight is 4,549.5 pounds. That's just below 5,000. When side length is 4 feet, the weight was 10,784. That's above 10,000. You can start to see that things are jumping pretty quickly now. And when side length was 5 feet, the weight was 21,062.5, which is above 20,000. So again, you can see that these points started low, but as we started to increase, it starts to go up pretty quickly. So just according to our graph here, is it linear? No. For part B on the next page. How is W equal to 168.5 S cubed different from a linear function? Well, again, as the side length increases by 1 foot, the weight does not increase by a constant amount. If it was linear, it would increase by a constant amount. Just notice how far this jumps pretty quickly. Going from 2 feet in side length to 3 feet, you go up by a little more than 3,000 pounds. But then going up from 3 feet in side length to 4 feet, it's going up by 5,000 pounds. And then from 4 feet to 5 feet, it goes up by almost 10,000 pounds. So that's not a constant increase. So now part D. A contractor has equipment that will allow him to handle stones that are as heavy as 4,000 pounds. How large can those stones be? Meaning, what is the length of the side of the stone? Estimate this from the graph. So let's go back to our graph. 4,000 pounds is as much as his equipment can measure. So this is below 5,000 pounds. If you're wondering what's halfway between 0 and 5,000, it's 2,500. So 4,000 is somewhere close to 5,000. We have a data value that's pretty close to that too. Remember that 4,549.5 pounds was how much we got for a side length of 3 feet. So we expect that how big can the stones be? Has to be something less than 3. So we would expect side lengths a little less than 3 feet. Part E, what size stones are too heavy for the contractor's equipment to handle? Use the graph to solve this problem. Connecting the points on the graph with a curve may help. So again, you can think this is related to what we were talking about just in the previous question. If it's any side length above what we just said, then it would be too heavy. So any side length above, and again, we can just estimate 3 feet. If you wanted to get a little bit more of an exact answer, you'd have to use the equation. But that's going to involve a different function that we don't really need to talk about as we finish up this lesson. So now to finish up, the next step. We have seen two power models, y equal a times x squared and y equal a times x cubed. In both examples, a is a constant. A constant means in this case that a is a number. These functions are examples of power models. We call the functions power models because both functions contain a variable term raised to a power. Y equal a times x squared is an example of what is called a quadratic model. And y equal a times x cubed, that is an example of a cubic model. So first, what is the similarity between proportional relationships and power models? Power models are proportional. Notice that these power models are similar to the proportional models that we studied in lesson 11.1.3 because both x and y are 0 together. That's really the easiest way to spot a proportion. If one variable is equal to 0 and right along with that the other variable is equal to 0, that's a proportion. This occurred for the 3 examples in this lesson. A ball of diameter 0 inches would take 0 ounces of paint to cover. A ball that travels 0 seconds will travel a distance of 0 meters. And a stone of length 0 feet would weigh 0 pounds. So now here we can summarize everything that we've seen. Determining whether a power model is linear, quadratic, or cubic. Linear, quadratic, and cubic models are proportional models. Here are some basic rules about linear, quadratic, and cubic models. These rules help us understand how to determine the appropriate power for the power model by looking at what happens when we double the input value. So number 1, if doubling the input value, like x, doubles the output, recall 2 to the first is equal to 2, the model is a linear model with power 1, which has the form y equal to a times x to the first, or just simply y equal a times x. This is what we learned in section 11.1.3. Part 2, if doubling the input multiplies the output by 4, because 2 to the second power is 4, the model is a quadratic model with power 2, which has the form y equal to a times x squared. And then part 3, if doubling the input multiplies the output by 8, because 2 to the third power is 8, the model is a cubic model with power 3, which has the form y equal a times x cubed. So it's just this one little trick of doubling the input and seeing what happens to the output. If it doubles, it's linear. If it's multiplied by 4, it's quadratic. If it's multiplied by 8, it's cubic. So now let's try that out. Number 5. The data in the following questions fit mathematical models very closely. For each question, determine the power of the power model that best describes the pattern in the table or graph. Part A. The following graph shows the weekly salary of an employee based on the number of hours worked in a week. So here we can see a horizontal axis for numbers of hours worked per week, and then a vertical axis for weekly salary, and then some dots that are graphed. First of all, take a look at those dots. Do they appear to be in a straight line? Looks like it. So we already have a suspicion that this is probably a linear model. But how about this? Let's take an example. Let's say that the number of hours worked per week is 8. How much weekly salary does this person get? Well, find the 8 on the horizontal axis, follow that up to the graph. There's a dot. Now follow that over to the vertical axis. How much money is it? $160. So if hours worked is 8, weekly salary is $160. Now let's use what was stated in the you need to know box. Let's double the input value. So double the hours worked. If we double the hours worked, that's double of 8. So what's 2 times 8? That's 16. So if the next week this same person works twice as long, 16 hours, how much money do they make? Let's go over to 16 on the horizontal axis, follow it up, and then follow that over to the vertical axis. And what do we get? $320. So in this case, the weekly salary is $320, which is double 160. So notice what happened. When we doubled the input, the amount of hours worked, we doubled the output, the weekly salary. So this is linear. Okay, now on the next page, part B. All across the country, people and businesses are beginning to use wind power as an energy source. Wind power uses wind to generate electricity. Several factors determine the amount of electricity measured in kilowatt hours per year, which is abbreviated K, capital WH for kilowatt hours/year, that is produced by a wind turbine. These factors include the diameter of the wind turbine and wind velocity, which is measured in miles per hour, or mph. The table below shows annual wind energy produced by a wind turbine with a 10-foot diameter for several different wind velocities. So the first column gives us wind velocity, 10, 12, 15, 20, 25, and 30. And then energy per year is the second column, measured in kilowatt hours per year. If you have a wind velocity of 10 miles per hour, that gives you 1,328 kilowatt hours per year, and then those increase as the velocities increase. So we want to see if this is linear, quadratic, or cubic. So to answer this, it's as simple as what we just did at the end of the previous question. Let's just pick a particular wind velocity and then double it and see if the energy per year doubles, or if it's multiplied by 4, or if it's multiplied by 8. So I'm going to pick wind velocity 10 miles per hour, which gives energy per year 1,328. So now what is double 10? If we double 10 miles per hour, it's 20 miles per hour. So now let's take a look at where the wind velocity was 20 miles per hour. That gave us an energy per year of 10,624. So is that double 1,328? Well, let's see. The output for 20 miles per hour is 10,624. Let's see if that's double 1,328. So I'm just going to take my calculator and take 1,328 and multiply it by 2. No, I only get 2,656. Well, what if I take 1,328 and multiply it by 4? Still not enough, 5,312. So what does it seem like we've got? If you take 1,328 and multiply it by 8, you get 10,624. So this is a cubic model. So if we double 10 miles per hour, that gives us 20 miles per hour. But what happened to the energy per year? It was multiplied by 8. You could try this also if you take the wind velocity of 15 miles per hour and double it to 30. See what happens to the energy per year with those two. And now finally, part C. The volume of a circular pipe depends on the radius of the pipe and the length of the pipe. The table below shows the volume of a pipe that has different sized radii. The pipe has a length of 6 inches. So the first column gives us radius of pipe measured in inches, and then the second column gives us volume of pipe, which is measured in cubic inches. Just like the last example, I'm going to pick a particular radius. So I'm going to pick radius of 6 inches, which has a volume of 678.24 cubic inches. And now I'm going to double it, which means 6 times 2, which is 12, which has a related volume of 2,712.96 cubic inches. So radius of 6 inches doubled to 12 inches. Now look at the volume. The volume for 6 inches was 678.24. Changes to 2,712.96 cubic inches. So first of all, if I take 678.24 and multiply it by 2, am I doubling the volume? No. So this is definitely not linear. What if I take 678.24 and multiply it by 4? That gives me 2,712.96 cubic inches. So how is it changing? It's multiplied by 4. So this is not linear, this is not cubic, this is a quadratic. And that finishes this lesson, and that finishes Math 21B. So the word for this lesson is done, because you are done with this class.